Hello, my name is Ghazal. I'm a member of Inclusive Interaction Lab at University of California, Merced. Today I'm going to present our project, TiltWalker operating a telepresence robot with one hand by tilt controls on a smartphone. Telepresence robots facilitate our interaction with a remote setting where our presence is not possible. However, there are challenges in maneuvering the telepresence robots from a distance. There are a variety of commercial telepresence robots available for use, including these examples. The Omni telepresence robot was the robot we used in this project. Most client applications designed for controlling telepresence robots don't provide relevant information or use effective interaction methods. More specifically, mobile clients have too many interactive elements that either leave little room for camera feeds or partially block them. The application on the right is the default application for the telepresence robot we use in our study. In these interfaces, it is very likely for users to make errors since the interactive elements are small and very close to each other. Errors in controlling robots can lead to collisions, especially in crowded environments. Our goal was to design a minimalistic interface that is not blocked with interactive elements, provides clear views of two camera feeds, can be operated with one hand, and uses phone directional tilting gestures for controlling telepresence robot. We developed TiltWalker, a web platform to provide all these features. TiltWalker has two modes, one for controlling robot's camera movements and the other for driving the robot. Single tap and hold to activate navigation mode, and double tap and hold to activate neck mode. We conducted a user study to find out if it is possible to distinguish between different gestures using the accelerometer data and identify the most comfortable and effective directional tilting and twisting in both standing and seated positions. We also wanted to examine how much users can tilt and twist the phone without compromising their comfort and the legibility of the display content. To be more specific, we were looking for tilt upper and lower bounds and speed. We had 12 participants. We included all the gestures mentioned in the study. We asked them to perform the gestures at three different speeds, low, regular, and fast, and in two different positions, seated and standing, in counterbalance order. For all our studies, we used an Omni telepresence robot that includes a 4K forward-facing camera, a wide-angle downward-facing camera, an HD IPS touchscreen, a Samsung Galaxy S6 Edge smartphone to run the web application viewed on the Firefox for Android web browser. In the first user study, we asked participants to hold the phone with their dominant hand and follow the instruction in the web application. The web application displayed static images of two camera views of the robot and provided instructions on which gestures to perform and at which speed. The instructions used color-coded textual and graphical cues. These plots show the average displacement angle per time over all trials for all participants during the regular speed condition. By looking at the plots, we can clearly see that there are substantial peaks in the plot when users perform tilt gestures around axis Y, twist gestures around axis Z, up and down gestures around axis X, so it was possible to distinguish between the tasks. Physiologically, it is slightly more difficult for people to perform twist than tilt and up and down gestures. We found this from the feedback we collected after the study. So we picked right and left tilt, down and up for TiltWalker. Statistical analysis identified a significant effect of task on highest peak in the respective axis and no significant effect of speed. We used the phone down and up gesture to drive robot in forward and backward directions, and phone right and left tilt to turn robot to right and left directions. Using the results of this user study, we found the lower and upper bounds of angles and angular velocity for performing tilt gestures without compromising user comfort and the legibility of the display content. We needed to find a method for mapping the displacement of the mobile phone to robot movements. We investigated two position and two velocity controlled functions. The position controlled method increases the robot's speed only by tilting the phone farther, while the velocity controlled method also considers the tilt speed of the phone. For the mapping functions, we picked two sigmoid functions, one quadratic function and one logarithmic function. Sigmoid function is appropriate to maintain values within a range since both tilt angles and the robot's speed have upper and lower bounds. Quadratic function is good to magnify the values and the logarithmic function reduces the impacts of tilt angles on the robot's velocity. We conducted a user study to find out which mapping function performs better in terms of precision, accuracy, and user preference. 12 participants took part in this user study. Participants navigated the robot through an obstacle path to a target and back in reverse motion using the four mapping functions. The telepresence robot was kept within sight since the application was not ready yet. We recorded the time users took to navigate the robot to the target from the initial position. We also logged error when the robot deviated 0.3 meter from its path, moved or turned in wrong direction, or stepped over an obstacle. In terms of task completion time, the velocity-controlled F1 was the fastest method. Velocity-controlled F2 was the second fast method, and the effects were statistically significant. In terms of the error per task, the position-controlled F2 and velocity-controlled F1 performed better, although the effects were not statistically significant. We collected user responses to 5-point Likert scales asking them to rate the speed, accuracy, learnability, and ease of use of the examined functions. Subjective evaluation found the velocity-controlled F1 easier to learn and provided much smoother changes in velocity than the other functions, although the effects were not statistically significant. Using the results of quantitative and qualitative studies, we decided to use velocity-controlled F1 mapping function in TiltWalker since it was more balanced, fast, relatively accurate, and users liked it the most. As you can see, the default OmniLab application has too many interactive elements. The forward and navigation cameras are small and it is difficult to see on a mobile device. TiltWalker, on the other hand, has a minimalistic interface that does not have many interactive elements and provides a clear view of the two camera feeds. The top part displays the forward-facing camera view, and the bottom part displays the downward-facing camera view. A menu bar is placed on the top of the display, which contains icons, mic, camera, call, settings, and battery level. The other feedback is a speed and direction gauge. The needle of the gauge indicates rotation direction, and the colors of the panel indicate speed. In the color wheel, cool to hot colors represent the lower and the upper bound of speed. In the final user study, TiltWalker was compared with the baseline application in a person following scenario. 12 participants took part in this user study. Participants had to navigate the robot through an obstacle path. The robot had to follow a human walking in front of it toward the target. Every time, robot started from a different distance to the person, 1.5, 4.5, and 9 meter, and had to catch up with the person and maintain a distance of 1.5 meter. On the right is a map of the path that the robot had to follow. Robot had to go around 3 obstacles of different sizes on its path. The telepresence robot was out of sight in a corridor about 100 meters away from the lab, and participants stayed in the lab. We recorded the same performance metrics as previous user study. The only difference was that this time, instead of deviation from straight line, the distance less than 0.5 meter from person was considered an error. The average task completion time and error rate for the TiltWalker was less than the default method, and the effects were statistically significant. We also collected user responses to 5-point Likert scales, asking them to rate the speed, accuracy, learnability, and ease of use of the examined methods. Participants preferred TiltWalker's feedback and its tilt-based interaction significantly more than those of the default method. Participants were also asked to complete a NASA TLX questionnaire. Statistical analysis found a significant effect of method on mental, physical, and temporal demand and effort, but no significant effect on performance or frustration. We presented TiltWalker, a mobile client for controlling a telepresence robot with one hand by performing tilt gestures. TiltWalker was designed based on a series of lab trials and user studies. In the future, we will evaluate TiltWalker in realistic crowded environments such as a shopping mall, since we expect it to be more efficient in these scenarios than the default clients. We also want to explore scenarios in which the operator slows down the robot and talks to the person through the robot. Furthermore, we try to make the robot semi-autonomous to facilitate obstacle avoidance. Thank you.